Will NASA's Sunbeam drive soon be taking us to distant star systems? Due to the vast distances that prevail in space, the dream of interstellar travel seemed like an unfillable wish for a long time. But now, experts have developed a revolutionary concept that should finally make the leap to distant worlds a reality. While the double star Alpha Centauri, which is only 4.34 light-years away, seems unreachable with our current means, the new propulsion technology could bring a probe to it in just 40 years, a formidable challenge. At first glance, the background to the new Sunbeam drive seems quite simple. As we all know, gas stations in space are in short supply. But what if we gave a spacecraft a component that supplies it with the necessary propulsion energy from the outside during its journey? Well, that is exactly what the new NASA concept envisages. The spacecraft will not carry its fuel at all. Instead, it will be supported by an external platform that provides the energy supply via a particle beam. Why this particular form of propulsion could achieve the decisive breakthrough in the field of interstellar travel becomes clear when we consider the incredible speed increases possible with this method. Recently, the Parker Solar Probe became the fastest man-made object of all time when it approached the Sun at a mind-boggling speed of 692,000 km per hour, an undoubtedly impressive feat, but it pales in comparison to the speed of light, estimated at around 1.08 billion km per hour. With Sunbeam, it's possible to accelerate a probe to 10% of this universal maximum speed. In other words, the spacecraft could race through space at a good 100 million km per hour. But how is that even possible? The answer lies in relativistic electron beams. Electrons accelerated to nearly the speed of light generate enough power to propel even a 1,000 kg probe across interstellar distances. Once this approach is realized, the Alpha Centauri star system, 4.34 light-years away, will no longer be tens of thousands of travel years away but only 4 decades. This is particularly interesting from a research perspective because Alpha Centauri, together with the star Proxima Centauri, forms a super-triple system that may even harbor a habitable planet, Proxima b. At first glance, 4.34 light-years may not sound like much. But to grasp the vast distances in the cosmos, consider this example: no other man-made objects have traveled as far into space as the 2 Voyager probes. Since their launch in 1977, Voyager 1 and 2 have covered an astonishing 2,481 and 2,074 billion kilometers from the Sun, and that's still not even a single light day. Despite their advanced age, these probes are by no means slow, traveling at around 61,000 kilometers per hour. Yet, compared to 100 million kilometers per hour, Voyager's speed seems more like a snail's pace. So how does Sunbeam technology actually work? The core of the propulsion system is the so-called solar station, a stationary platform placed near the Sun. It remains in place using light pressure and solar magnetic fields while firing a high-energy electron beam at the probe, which is protected by a massive solar shield. When the focused electron beam hits the probe, it transfers momentum, continuously accelerating the spacecraft without relying on its own fuel. The longer the beam acts on the probe, the greater the speed boost. But shouldn't the electrons eventually disperse into the vastness of space? Fortunately, they don't. While electrons usually repel each other, they exhibit remarkable behavior when accelerated to relativistic speeds, near the speed of light. This phenomenon, known as the pinch effect, is based on time dilation. In simple terms, moving clocks run slower, and in the case of Sunbeam technology, this prevents the electrons from drifting apart. As a result, the beam remains stable and focused even over enormous distances. The dream of interstellar travel is not new. In fact, the idea of accelerating a spaceship using an external beam has been explored before. Launched in 2016 with the participation of renowned scientists like Stephen Hawking and Freeman Dyson, the Breakthrough Starshot research project also proposes a spacecraft that receives an external energy boost. However, while Sunbeam is designed to propel a 1,000-kilogram spacecraft, Breakthrough Starshot relies on a tiny, gram-scale probe equipped with a light sail and powered by a laser. Breakthrough Starshot envisions a vast array of powerful lasers forming a 100 gigawatts beam to propel the mini-probe sail over a distance of 20 million kilometers. In contrast, the Sunbeam approach sounds much more promising, as it would allow us to send a fully equipped research probe to Alpha Centauri. This would enable us to determine whether Proxima b truly has the potential to support life. Although the exoplanet is likely tidally locked, meaning one side is always in darkness while the other faces perpetual daylight, a narrow twilight zone might exist between these extremes, possibly harboring liquid water. If life already exists on Proxima b and is detected by an interstellar spacecraft, it would undoubtedly be one of the greatest astronomical discoveries in history. But what's stopping NASA from moving forward with Sunbeam? As is often the case, several challenges remain. One major hurdle is the energy supply. To accelerate the probe, the relativistic electron beam must first be generated. That's only the beginning. The high-energy beam must also be precisely aligned with the probe over vast stellar distances. Even the smallest deviation could cause the beam to miss the spacecraft, rendering the mission a failure. Moreover, as the probe moves farther away, maintaining the beam's effectiveness requires increasing amounts of energy. Since the solar station is to be positioned near the Sun, it must be built from materials capable of withstanding extreme heat and radiation. Fortunately, past technological advances suggest that many of the necessary foundations for revolutionary propulsion already exist. For instance, the Large Hadron Collider at CERN generates beams with higher energy than required for Sunbeam. Similarly, modern particle accelerator guidance systems could provide precise targeting in space. Additionally, materials used in spacecraft like the Parker Solar Probe have already demonstrated the ability to withstand the Sun's harsh environment. When it comes to power generation, scientists propose using thermoelectric generators to convert intense solar heat into electricity. However, a crucial limitation is that no existing technology can currently enable these cosmic solar power plants to function at the required scale. As a result, the Sunbeam concept remains theoretical, and even the most optimistic projections estimate that at least 20 more years will pass before the first prototype is launched. Beyond the technical hurdles, another significant issue is funding. Developing a completely new propulsion system would cost several $1 billion, and it's unlikely that NASA will shoulder the entire financial burden alone. A more realistic scenario would involve international space agencies collaborating and securing private investment. While patience is required before Sunbeam becomes a reality, it is by no means an impossible dream. Future breakthroughs in various scientific fields could accelerate its development. History has already shown how quickly technology can advance. After the world's first powered flight on December 17, 1903, it took less than 70 years for humans to walk on the Moon. Who knows? We may still witness the launch of the first interstellar research probe within our lifetimes. It's exciting to imagine what interstellar exploration could mean for humanity. If Sunbeam drive or similar propulsion technologies become a reality, we could finally begin the journey beyond our solar system, not just as dreamers, but as true explorers of the cosmos. Imagine a future where probes equipped with advanced sensors, artificial intelligence, and high-resolution imaging systems reach distant star systems, transmitting data back to Earth about potentially habitable planets, exotic exoplanetary atmospheres, and even signs of extraterrestrial life. The discoveries could reshape our understanding of the universe and our place within it. However, interstellar travel isn't just about propulsion. Even if we can send probes to other star systems, communication remains a major challenge. Signals traveling at the speed of light would still take over 4 years to reach Alpha Centauri, making real-time interaction impossible. Scientists are exploring quantum communication, laser-based data transmission, and other futuristic methods to bridge this gap, but practical implementation is still far off. Another challenge is ensuring that an interstellar probe remains functional for decades. Spacecraft must endure extreme radiation, micrometeoroid impacts, and the harsh conditions of deep space. Advances in self-repairing materials, AI-driven maintenance systems, and ultra-efficient power sources will be crucial to overcoming these obstacles. Beyond robotic probes, the ultimate goal of interstellar travel is sending humans to distant worlds. While Sunbeam technology is not yet suited for manned missions, it could serve as a stepping stone to more advanced propulsion systems that might one day carry astronauts beyond our solar system. Concepts like fusion propulsion, antimatter drives, or even theoretical warp drives are being studied, but they remain in the realm of speculation and distant possibilities. For now, Our best bet is to refine technologies like Sunbeam and work toward practical, near-term interstellar missions. Even a single successful probe reaching Alpha Centauri would be a historic milestone, a testament to human ingenuity, perseverance, and our relentless drive to explore the unknown. The coming decades will be crucial. If funding, international cooperation, and technological breakthroughs align, we may witness the first steps toward becoming an interstellar species. And who knows? Perhaps, within our lifetime, we will receive the first images of an alien sunrise from the surface of a distant world, captured by a probe powered by the very same sun that gave birth to us.